I understand what an equation means if I have a way of figuring out the characteristic of its solution without solving it. Paul Dirac. I understand what an equation means if I have a way of figuring out the characteristic of its solution without solving it. Wow. If you take a piece of photographic film and expose it to the sunlight itself is not charged, nonetheless it can interact with electrons. The sunlight can expose that film, ripping apart, making little ions. Then you develop the film, and it looks back where it's been ionized. So people developed particle detectors, and a particle detector is any device that you can think of that is capable of showing you evidence of the passage of the invisible. Remember, these are submicroscopic particles. The way you could do that, for example, would be to take a photographic plate, and send a charged particle goes running through it as when light goes through it, and it will leave behind a little trail of ions. You develop that film and you'll see a little black line. In fact, that little black line, the intensity of that line will tell you information about the energy and the character of the particles. A more highly charged particle will leave a thicker line. You can learn about the particles by looking at these developed plates. These plates were called emulsions. They were like a photographic film, a little bit thicker. The technology of the emulsions developed in the 1920s and 1930s and was used for many years as particle detectors. Haha. There were other technologies that were developed. For instance, the bubble chamber. The bubble chamber was a little bit more of the mechanical device. Imagine taking some gas in the chamber. There are bubble chambers and there are cloud chambers. Let me talk about cloud chambers first. In a cloud chamber, you take some vapor and you'll pull a piston out very quickly. This gas is present in the chamber. It has cooled because you expanded the piston and the cool gas really wants to condense. Now it turns out that when you really want to condense, it's nice to have some place to condense. You might condense along the walls, or if there is an ion trail in there, that's where you are going to condense. So here is the idea. An electrically charged particle goes flying through, perhaps a cosmic ray. You pull the piston, that little trail of ion is going to form a little chain of water droplets. Water, or whatever the materials is in your cloud chamber. Those water droplets then are visible. They are not microscopic, even though the particles that made them was. So this is a way take a picture and you see a little line, just like the photographic immersion. There are various advantages and disadvantages to both of these. The cloud chamber is three-dimensional and can be quite large, unlike the emulsions, which are fairly flat and tend to be small. The bubble chamber is like the cloud chamber, except instead of the water condensing where the ions are, imagine that you had something liquid already that was superheated. It really wants to boil, so bubbles are going to form. Where are they going to form first? They always form on impurities or edges. So if there are ions in there, they are going to form light around the ions, and once again you get a little line. It's like when you look up in the sky and you see this trail of jet airplane. The jet airplane may be too small for you to see, but behind it is a trail of exhaust. The clouds, well, there are no clouds up there yet, but there is a water vapor. It's cold up there, and the water vapor really wants to condense and form a cloud. It will tend to do when there is a place for it to do it, which is on the exhaust trail. Ah, now I see. So you look up in the sky and you see this beautiful line which tells you where the airplane has been, and if you are really skilled, you might have figured out what kind of an airplane it was by looking at the characteristic of the line. That line. It's the same thing with the cloud chamber, which was invented in 1911, and the bubble chamber, which really wasn't developed into the technological usefulness until the 1950s. You are getting photographic images, and what you get are images which look something like this. Here is a picture of bubble chamber, and you can see trails of particles. It looks like a big nest because there was a whole bunch of particles interacting and knocking into nuclei. Now you've got to try to take that picture, piece it apart, and figure out. Okay, what was in there? By looking at the density of bubbles, I can figure out how electrically charged it was and how energetic it was. If you immerse this whole thing in a big magnet, if you just put a magnet next door, then the magnetic fields will cause the electrically charged line to bend. The amount of the bending teaches you something about the particle's properties. The more energy and more momentum it has, the less it bends, right? Because it's basically just plowing on through in a straight line, and the lower its energy, the more easily the magnetic field make it go in a circle. You'll see some low energy particles that form little corkscrews in these pictures, so you can begin to piece together in a bubble chamber or cloud chamber or immersion the details of the process that you saw. Wow. This was the experimental world of the 1920s and 1930s. They might take a big balloon and launch some emulsions way up high in the air so that the cosmic rays hit them, or they might take some radioactive material and put it next to bubble chamber or a cloud chamber in earlier days. One of the most important things that the people were trying to look for was Mr. Yukawa's pion. Yes. I mean, they were looking for a trail with a certain very well-defined characteristics. They thought they knew its mass. They thought they knew its electric charge. Mr. Yukawa predicted in his original paper that his virtual particle could be positive or negative or neutral. There were three-dimensional kinds of pion. We call them the pi plus, the pi minus, and the pi zero for obvious reasons. For shorthand. This was a prediction of Yukawa's theory, and you should be able to see a trail in a bubble chamber picture. I should say cloud chamber because bubble chambers didn't come until the 1950s. That's what you are looking for. In the 1930s, around 1937, I believe such a trail was seen. It was a charged particle. It has a mass predicted by Mr. Yukawa. It was intermediate in size, a little lighter than the proton and a little heavier than the electron. But this particle didn't quite make sense. People look at these trails, and in some respect, it seems like this predicted particle of nature. Right. But in other respects, it didn't. The most important thing, the glaring issue was the pions were invented to explain the strong nuclear force. Pions should be strongly absorbed by nuclei. That's what they are for. That's why they were proposed. Yet, in these bubble chamber, cloud chamber pictures, the particles that you saw begin at the one end of the chamber and went all the way through. Actually, the original picture of the muons came from the emulsion. Wow! Emulsions. In fact, they started at one end and went all the way through to the other end, hardly interacting at all. What did they look like? They looked like electrons. electrons also just cruise on through. They are electrically charged, so they have a little trail of the bubbles behind, but that's about it. They don't hit the nucleus and cause some explosion or reaction of any kind. Haha. So what they were seeing, this new particle didn't appear to be behaving the way Mr. Yukawa's pion behaved. So people stretched their heads and they started to collecting more and more data, and they said, look, we can't call these things the pion because it's not Mr. Yukawa's particles. Let's give it a new name. Haha. It's a something on. It's something on. Okay. So we come up with another Greek letter. We are just going through the alphabet now. It's a muon. Muon. I have no idea why they picked the Greek letter mu for these things. It's just a muon. That's its name. The muon is a big mystery particle. It's discovered in the emulsions, but why is it there? What role does it play? It's like a heavy electron. It turned out, in both positive and negative charges. There was no evidence of electrically neutral one, only positive and negative muons. The mass was this intermediate mass in between the proton's mass and the electron's mass, and they were radioactive in the following sense. Every now and again, you'd see a muon decaying at the end of its track into an electron. So this muon was radioactively unstable. It could transform itself into an electron, and this was all just a big puzzle. Wow. It was the first time that a brand new particle, a subatomic, fundamental particle had been discovered, and nobody had a clue about why it was there, what role it was playing, what it meant in a certain sense. This is how particle physics began to appear more and more over the next couple of decades. People were finding particles, and they were mystery particles. Wow. We are going to come back in this course and revisit the mystery of the muon to try to understand what this thing is and what role it plays. I have to confess that even today, although we know all about muons and we use them in the technology, muons are constantly present. Wow! They are present in the cosmic rays, they are present in the accelerators, but we don't really have a completely deep understanding of why the muon is there. Ha ha ha. A famous physicist, I. Ravi, said, "Who ordered that? Who ordered that?" It was quote, like you're in the restaurant and a bunch of people are there and this dish comes. The mystery dish. Who ordered that? That's a muon. That's a muon. Oh, I like you, Ravi. I love you. Who ordered that? So funny. It was another 10 years before Mr. Yukawa's pion, which made sense. It was predicted, it was expected, was indeed discovered. It turned out that the reason we hadn't seen it is they are produced very easily, very strongly in the upper atmosphere, and then they hit nuclei very quickly because they are strongly interacting particles. They tended to not to make it down to our laboratories, so we needed higher energies and particles accelerators before we are able to actually see those pions, the particles that Mr. Yukawa had predicted. So, at this point, we have a developing scenario in the world of the nuclear physics. We've got our quantum mechanics, which is a mathematical framework that allows us to describe these phenomena quantitatively. We have protons and neutrons and electrons, and now we've got pions that are expected but not yet seen until the late 1940s, early 1950s, and the muons, which are seen but not expected, so the world of the particle physics is beginning to develop. There are new species of particles that are mysterious and unexplained, and people are getting really curious. What are these things? What are their properties? I would say the discovery of muon is, in a real sense, the birth of particle physics. It's a transition from just studying nuclei and their forces to saying, hey, there is other stuff going on. There are actually new particles in the world, and we've got to understand them. Ha ha ha, thank you.